Okay. Good morning, everyone, and thanks for coming to our 10th recitations of 2100. So today we're going to cover a bunch of problems related to combinatorics. I also have some problems on relations towards the end, but those are just kind of more of a backup slides. We'll see if we'll get to there. We'll do quite a lot of breakout rooms. I think they'll work well with combinatorics because these problems are, I guess, always a little bit tricky, and it's easy to come up with kind of different solutions. So I think it'll be interesting to discuss which one is the right one and why, and so on. So that's the plan for today. Before we dive into that, as usual, I have a couple of announcements to make. So we are almost done grading quiz 3, and I expect we'll be able to post quiz 3 grades maybe even by the end of the day today, and if not, then tomorrow. So I will also post the breakup of the grades and so on. One thing I want to mention is that my foot got stuck in the chair. TAs, during the discussion sessions last week, a couple of you brought up some concerns about the length of quiz 3. And maybe it was, too much work to solve it in 1 hour and so on. So we will look into that. We will look into grades, and we'll take this into account when making quiz 4. And one more thing I will say, quiz 4 and 5 do tend to be a little bit easier, just because I think the material is also easier. What else about quiz 3? Oh yeah, so again, we took your feedback into account, and we started last time solving quiz problems during discussions and also on Piazza. And so if you're interested in the correct solutions for quiz 3 problems, come to discussions on Thursday, and also look for Piazza posts. Okay, so I think that's quiz 3. So homework 4 was due this past Friday. We will try to grade it by the end of this week. There's a lot of grading, and it's hard to do all of these in just a day or two. And then we released homework 5, which is on combinatorics, which is what we'll talk about today. So take a look at it, start working on it. And then finally, okay, so next week is a little bit special because elections are on Tuesday, on November 3rd. And as per college guidelines, we will not have synchronous recitations that Tuesday. So, you will not have to join at this set time next Tuesday. Instead, you can use that time to go out and vote. I think it's a good year to do it. And one thing I also want to mention is that you can still register for voting in person if you haven't done that already. So the voter registration deadline online has passed, but you can register in person. So, okay, there will be no synchronous recitations, but we will post recorded recitations. So there will be recitations to watch this week, except they won't be synchronous. Because of this, again, as per college guidelines, there will also be no office hours on Tuesday and Wednesday. So TAs will not have office hours, except I will have mine on Wednesday morning. So I figured, we're not going to force TAs to have office hours, but I'll do mine. So, Wednesday morning, if you want to discuss whatever CS2100 issues you have, please come to my office hours. We can also commiserate about the elections as well, if you're up for that. So these are my announcements. Any questions about any of these? Okay. So as usual, you can ask your questions.
Maybe I had a question.
Or even better, you can just unmute yourself and ask the question. There is only around 30 of you joining these days, and so that won't cause a lot of confusion. Okay, so before we start with our problems, let's review some basic rules for counting. So in the lectures, we covered a couple of different rules. So we covered the rule of products. So that applies if you can select values individually, then you can multiply the counts. Then we have rule of sums. So we can apply a rule of sums. We can split the problem into the joint sets, and then we can add the counts of each individual set. We have rules of sums with overlap. The rule of sums applies if there is no overlap between the split. If there is an overlap, then we must subtract the count of the overlap. Oh, it seems that I missed the question. Sorry about this.
It was a spoken question.
Okay.
Oh, was it me?
Yes.
Yeah, I always have to set my speakers. Anyways, long story. I have a couple of sets of speakers and I chose the wrong one. So sorry about this. So could you please repeat your question? I didn't hear it.
Suzanne, I just want to know exactly when the office hours were or where to go to find out.
The office hours, the ones I mentioned, my office hours?
Yeah, and the recurring TA's ones for every week as well.
So if you go to Canvas, there is if you go to modules, there is a couple of links to various pages in the beginning of the modules. And one of them is getting help in CS2100. And if you click on that, there's a whole schedule of office hours that repeats every week. So I don't know off the top of my head. I mean, there is a lot of them. Like every day, we probably have 6-7 hours of office hours or something like that. So, so if you go there, it's easy to find them.
Okay, thank you.
Yeah. And please come to office hours. They're kind of pretty underutilized. So, usually there is no big lineup of students waiting for office hours. So, if whatever you're struggling with, please do come to office hours. Any other questions? Oh, and Mark just posted a link in the chat. Thank you, Mark. Okay. Okay. Okay, let's come back to this. So rules of sunset overlap, we covered that. Rule of complements. We will actually see this one and keep it in mind when you are working on the problems that we'll go through. So it says that we can count objects with a certain property by counting the objects without the property subtracted from the universe count. And I know this sounds kind of abstract now, but we'll see in the problems how to use it. And then we talked about 4 different structures and how to count the number of objects that belong to the structures. So we have ordered list of n r from n elements, that's n to the power of r. We have permutation of length r from n elements, that's p n comma r. Then we talked about combinations and how to derive this expression for counting combinations. So in combinations, the elements the order of the elements does not matter. And we denote the number of combinations with C and R, and this is the formula for how to compute it. And then we talked about binary sequences and bags, and we derived this formula C of R plus N minus 1 comma R, which is a solution for all these different kinds of problems that are all equivalent. The most common one is the last one, the number of bags of R items with N item types. So this is what we covered in the lectures. And then we solved a couple of example problems. And now let's try to apply all of these on various counting problems. And this is really weird. Okay, I apologize. Let me somehow 2 problems disappeared. It's funny, I was just checking my slides. So this is practice problem 3. I also have problems 1 and 2 that somehow disappeared from my slides. I don't know why. So I'll double check that, but we can as well start with this one. Let's just start with this one. It's a little bit harder for starter problem, but that's okay. So let's see the problem. Okay, so we have Charlie and her girlfriend Amber go to lunch at the restaurant that offers 8 sandwiches on the menu and 3 beverages on the menu. So they order 1 sandwich and 1 drink each. And now we want to count how many ways can they order if they must order different sandwiches, but can order the same drinks, regardless of which one orders first. Okay, so we'll do breakout rooms to solve this. Let me just kind of note a couple of things about this problem. So one key piece of information is that we don't care which one orders first. So that means that the order doesn't matter of their order. So that's one kind of piece of information that helps you to know how to calculate this. And then another one is, so each one orders 1 sandwich and 1 drink. And the sandwiches must be different, but they can order the same drink. Okay, so I'll start breakout rooms and I'll give you a couple of minutes and you can try to solve this. Please feel free to discuss it amongst yourself. You can even work on it together. And then we'll reconvene and we'll try to solve it together. So let's do this. And in the meantime, I'll try to figure out where the heck my slides got lost. So please join the rooms.
When I was looking at it last night, there were some of them that were grayed out. I don't know what that means. They had...
Yeah, I don't know. I will take a look now. I mean, I was just working on them and they were all there, so. Oh.
Yeah, the graying out on mine goes away if I right click on it and choose hide slide.
Yes, I just fixed it. They were hidden for some reason. Yeah. Thank you, Mark. I fixed it. Hey, I'll send you to one of the rooms to help them. Do you hear me?
Yeah. What, room 2? I
Yes.
guess is the one I was assigned to.
Yeah, you can just join.
Okay.
Okay, welcome back, everyone. So I hope you managed to get some traction on this problem, and let's now look how we will go about solving it. So, we can split this into first computing the number of ways that they can order sandwiches, and then computing the number of ways they can order drinks. And then we use the rule of products to multiply these. So for sandwiches, what do we have? Their order must be different, and the order does not matter. So they're choosing two sandwiches out of 8 possible sandwiches. And we can kind of practice computing this a little bit. So that is equal to 8 factorial divided by 2 factorial times 6 factorial. And that is equal to 8 times 7 divided by 2 times 1. And so that's equal to 28. So I already mentioned this in the lectures. In the quiz, we will denote, we will tell you in the problem when we expect you to compute this final number and when it is okay to leave the result in a form that looks kind of like this. And this will depend on how big the numbers are. So this is a pretty tiny number when it comes to counting. And so it's easy to compute it. If this was like, 280,000 something, we would allow you to leave it in this format, and that will be totally fine and correct. Okay, so that's the number of different ways that they can choose sandwiches. Now let's look at drinks. Drinks are a little bit trickier.
We have a question.
Okay.
Do we have to always use the formula where necessary?
Do we have to always use the formula where necessary? I don't quite get the question. I mean, if we tell you, if in the question we tell you we expect you to compute the final number, then you have to, expand these combinations into the formula and compute it and so on. Oh, is that a question? I mean, I guess, you should not be, we want you to use the formula. Not calculators. Calculators and stuff like that are not allowed, right?
Okay, yeah, so do they have to choose R from N? Because if they can solve it in a different way without that formula.
Oh, I see. Yeah, that's a great question. So yeah, with counting, there is often different ways to arrive to the solution. And as long as you arrive to the correct solution, no matter how you got there, it's fine. So you don't have to use some particular way of solving it, right? And so you don't have to choose 8, 2, N, R. I mean, you can use some other rules to derive the result. And as long as the result is correct, that's totally fine. Okay, so when it comes to drinks, we have two possibilities here. So they either order the same drink or they order a different drink. If they order the same drink, there are 3 different ways of doing that because we have 3 drinks. And if they order a different drink, then that's the same as what we did for sandwiches. We have choose 3, 2 which is equal to 3 factorial divided by 2 factorial times 1 factorial, which is equal to 3. And now for drinks, these are two distinguished sets. And so we apply the rule of sums. So for drinks, we have 3 plus 3, which is equal to 6 different ways of choosing them. And so we have 28 different ways for sandwiches and 6 for drinks. And so by product rule, the final result is 28 times 6, which is equal to 168. Okay. Any questions?
Yeah, so couldn't they use the formula P3, 2 so as a permutation problem?
For calculating the number of drinks?
I think so.
That's a good question. So peak 3, 2 would not work because the order doesn't matter. So keep an eye on this important note here. So we do not care which one orders first, which means that the order does not matter. And therefore, that would be a wrong solution. You have to use combinations. If we said, the order does matter, so it does matter which one of them orders first, then permutations would be fine. But because the order matters, this would not be okay to use.
And I'll ask this for those not in chat. Why do we add them, get 3 plus 3?
Why do we add them? Because there are two different possibilities that are non-overlapping. So this is a sum rule. So they either order the same drink or they order 2 different drinks. And that's why you add them. And you multiply them because you have and between this. They ordered 2 sandwiches and they ordered 2 drinks. So then you use product rule.
And then one last one related to a previous question. Could we treat the drinks as a bag problem?
Could we treat the drinks as a bag problem?
Yes. Yes, you can.
Oh, okay. Thank you, Mark. Right, you have a bag of 2 items and you are filling it with 2 items. So yes, that will work as well. That's a good question. And yeah, like I said, there are often different ways to derive the solution. So this would be another way of deriving the solution. Good point. Any other questions?
Okay, so is it like when the order, or just when repetition does not matter, then you can use the rule of sums? When repetition does matter, then you use the rule of products?
No, so that's a good question. These are, how would I say, orthogonal. When you look at whether they're repetitions or not, you're deciding between, let me go back a little bit to, so when you think about whether they're repetitions or not, you are looking at which structure out of 4 structures we covered you're going to apply. So you have these 2, if you look at the bottom of this slide. So these 2, so permutations and ordered list of length R from n elements. These ones, sorry, we're talking about repetitions. So the first one allows repetitions, this one, and the second one does not allow repetitions. And combinations don't allow repetitions, and binary sequences or bags allow repetitions. So if you say, oh, I have repetitions, then you know either have to use bags or I have to use order lists. If I don't allow repetitions, either I use permutations or I use combinations. And the second key information is, does the order matter? For permutations and ordered lists, the order matters. For combinations and bags, the order does not matter. So if you remember in the lectures, it was this table which has order matters on x-axis and repetitions are allowed on y-axis. And you would choose among these 4 different types of structures based on that. And then you determine whether you use rule of products or rule of sums. I mean, that takes a little bit of practice, but if you have an or between 2 possibilities, so in this case, in terms of drinks, either they both order the same drink or they order distinct drinks, then you use sum rule. If you have and between possibilities, so in this case, it's two sandwiches and 2 drinks, then use product rule. That's kind of a general idea. Any other questions? Okay. Okay. So I managed to find my hidden problems. Slides were hidden. So let's do this one. I would say it's a little bit easier. We're not going to do breakout rooms for this one. I'm going to give you, let's say, 2 minutes to try to solve it on your own. And then I'll solve it for you. And please use these 2 minutes to actually try to do it, because that's the way to learn this. So we have 3 members of a 20-person office and they're carpooling. And so they exist on never working separately. Which means that whenever one is on a committee, all 3 must be on the committee as well. And now the question is, how many 7-person committees can be formed in this 20-person office? Okay. So let's try to solve this. So we have an office of 20 people. And these 3 people that they always have to work together. So whenever one is a committee, all 3 must be. And now, how many 7-person committees can be formed? So we don't distinguish between committee members, so the order doesn't matter. And there is also no repetition because we can't put the same person twice into the committee. So we're going to use combinations. Now we have to be careful about this problem. So so there are 2 cases here. So either these 3 members are on a committee or they're not on a committee. So when they're not on the committee, then how many committees can we form? Let me just, if they're not on the committee, then we can choose 20-person office, but these 3 are not. So we are choosing 7 out of 17. So that's when these 3 people are not on the committee. When they are on the committee, then the number of different committees we can create is choose 4 out of 17. So this is because when they're on the committee, then these 3 members are fixed. So we only have 4 members of the committee that we have to fill in. And we are going to fill them in out of 70 leftover people in this 20-person office. Okay. And now there is or between these, right? Either these 3 people are not on the committee or they are on the committee. And so we're going to use rule of sums. And so the solution is going to be choose 7 out of 17 plus choose 4 out of 17. Okay. Any questions about this one?
Perhaps why is it C17-4 instead of C17-3? If there's only 3 people in the carpool.
So, good question. So it's because we are filling in a 7-person committee. So this is the case when these 3 people are on the committee. So in that case, because you are filling in a 7-person committee and you fix these 3 on the committee, then there is only 4 leftover spots on the committee to fill in. And you are filling in these 4 spots. You're choosing for these 4 spots from 17 people because you're excluding these 3 that are already on the committee.
Okay, cool. Well, then why isn't the 17 a minus by 3 as well?
So because these 3 people, right? You kind of already put them on the committee. So you have this pool of 20 people and you have your committee here. And it's also a bubble. And first, what do? You put these 3 people on the committee. So you move them here. So you're going to have 3 people here now, and you're going to have 17 people here. And there is just one way to do this, right? Because it's these 3 people that are carpooling. And now you have to fill in the other 4 spots here from these 17 people. because you remove these 3 and you already place them on the committee. Okay?
Yeah, okay.
Okay. Other questions?
Yeah, so we chose the sum rule because these 2 choices depend on the other.
No, we chose the sum rule because these 2 choices are, how would I say, mutually exclusive. There is an or between them. So choice 1, these 2 choices are either we form a committee that does not contain these 3 members, or we form a committee that contains these 3 members. And we have to count the total of these 2. And because there is or between them, we use the rule of sums. You're choosing either one or the other, right? It's not an and. That's why you use rule of sums.
Yes, and they are also disjoint from each other.
Yes, they're also from disjoint, yes. Otherwise, we would have a more complicated rule of sums when the sets are not disjoint. Any other questions? Okay. By the way, as a side note, I like all the questions. I think this is good. But we are moving slowly to the problems. So in other sessions today, I will probably solve a different subset of the problems I prepared. So these are all recorded. So feel free to watch the recordings to see how we solve the other problems. So, okay, let's do this one. So you're playing a lottery where tickets have 7 order boxes, and each box can be any of 3 colors, red, green, or blue. So these are examples of the tickets, RRR, GB, GB, and RRR, GG, BB. These are distinct tickets. So we want to count 2 different things. So part A is how many possible tickets are there? And part B is how many possible tickets have at least 2 R's, 2 G's, and 2 B's. So I'll give you a minute or 2 to try to solve these, and then I'll do it for you. So think about, does the order matter? Are repetitions allowed? Stuff like that, and then try to solve this. Okay, we only have 5 minutes left, so I'll go ahead and then we'll take questions. So part A should be easy. So we allow repetitions and the order matters. So this is an order list. And therefore, the number of possible tickets is 3 to the power of 7. Okay? That's part A. Part B, it's a little bit trickier, and there are different ways to solve it. I solved it using this kind of way that we solved similar problems in the lectures that were related to words. I think one of them was Mississippi, right? How many different ways, different words you can create by changing the order of letters in Mississippi. And so what is the idea there? So the idea there is you have 7 spots. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Oh, and actually, let's think about pi b a little bit more before we dive into this. So we're looking for different ways that we can have tickets that have at least 2 R's, at least 2 G's, and at least 2 B's. Well, given that we have 7 boxes total, our only possibilities are 2R, 2G, 3B, 2R, 3G, 2B, or 3R, 2G, 2B. So these are the only ones that satisfy this B part. Each one of them is going to be equal. They're all equal, right? So if we count 1, we can multiply by 3 and we get the final number. Or we can use the rule of sums. It's either way is fine. So how do we calculate each of these? Let's look at 2R, 2G, 3B. So a common way to do this is you can think of it as first placing this, the algorithm first places this 2R into these 7 slots. Then it places 2G into the leftover slots, and then 3B into the leftover slots. So we can place 2R by choosing 2 slots out of this 7. And then we can place 2G by choosing 2 slots out of the 5 leftover slots. And finally, 3B, we are choosing 3 out of 3. So this is the different number of ways that we can do this first row here. You can calculate this out, and I'm running out of time. So do this at home. This ends up being 210. And so we have 210 for the first row. You'll get 210 for the second row as well, and 210 for the third row. And then the total number is the sum rule applied here. So you're going to get 210 plus 210 plus 210, which is equal to 630. Okay. Any questions? We have maybe 2-3 minutes left.
I do, yeah. So on that final choose 3 of 3, could you sub it out to be choose 3 of 2 and then multiply by 3 to account for the 3 choices that you could have, either a green or a red or a blue for that last slot that's not chosen?
Oh, and then not use rule of sums?
Yeah.
I mean, I see. Let me think about this a little bit. I mean, this will be very similar. I wouldn't quite say. I mean, I wouldn't. Yeah, if you replace this with choose 3,2, I wouldn't quite see why this would be the solution. You would get the same number, but I think the algorithm would be kind of broken. I wouldn't be sure like what this represents. So I don't think that would be a correct way to do it. Because here I started placing them, I'm choosing the slots where I'm placing these colors. And then you finish with kind of, well, no, now I'm also going to choose what my last color is. So I don't think that quite works, even though you get the same number. Any other questions? Okay. Okay. So then we'll stop here. Thank you for all the great questions. And like I said, I'm actually doing all four recitations today. So when we create the union of all these four recitations and the problems I'll solve there, I will solve all the problems I prepared. And it will also be non-overlapping. So that's how we'll do it. Okay, so thank you, everyone. We'll probably make another announcement about elections next week, so you don't forget about it. But yeah, there'll be no recitations like this in person next week. So thank you, everyone. Bye.